Hey guys, I want to look at an example of a constant velocity graph. We're talking about graphing constant motion. So we're going to be talking about constant velocity. So here's a problem. They give us a little data table. And here's our graph paper. The car travels at a constant 20 meters per second for 10 seconds. And you're supposed to fill in the table showing the car's displacement as a function of its time. The AP test likes to use that term function. It's very mathy. It's like math teachers use that type of thing. And the word function, I think, tries to scare people. It's basically saying there's a relationship between these two things, between displacement and time, right? So we have this car. It's going to travel at a constant 20 meters per second. My key word here is constant. If it's constant 20 meters per second for 10 seconds, then that means each second the speed of the car is 20 meters per second. This is like if you're driving on the highway and you put it in cruise. The idea behind cruise is that you don't have to do anything to the gas pedal and the car will go at a constant speed. So your speed doesn't change. Constant velocity. So what do we do first here? Well, we need to fill out our little table, right? So when we start the timer, if you're on the side of the road and you watch this car, it's traveling at a constant speed as we start the timer, so it's already moving. Okay, so we would see the car at some place. We'd have to decide what the origin is, okay, and wherever that car is, that is our zero, right? So down here, I guess this would be our 0 point. We'll talk about graphing in a second. So the question is, if the car is moving at 20 meters per second, each second, how far does the car go? I guess the question is, what does 20 meters per second mean? 20 meters per second means the car travels 20 meters every second. So after the first second, the car would be 20 meters away from whatever starting point that we had. After 2 seconds, so it's gone another 20 meters, right? Because each second it travels 20 meters. So that'd be 40 meters. And you just keep tacking on 20 meters every second. So after 10 seconds, the thing has gone 200 meters. 200 meter sticks away. All right, so then we'd have to graph this data. If you have time as one of your variables, it has to go on the x-axis. Time is always on the x-axis. The y-axis is the dependent variable, right? So we say that as time goes on, right, if we're standing on the side of the road with a stopwatch, and as time clicks by, what's the car doing? Well, it's getting further and further away. Okay, so the displacement is our dependent variable. I think one of the hardest things that kids have to do is learn how to graph. They don't always label their axes. Put the right axis, the right variable on the right axis. I found that a lot of my students don't know how to figure out what is the scale. So here's how I do a scale, right? And it has to be a consistent thing, okay? So if I look at this right here, I look at my time, right? All this data needs to be on this axis, right? My data is essentially starting at 0 and going to 10. So I have to have a even consistent way to start here at 0, and then over here I need to have essentially 10. I need all these numbers to fit into this space. So what am I going to do? Well, I'm probably going to count all these little dashes, see how many there are. And I can take that and divide by 10, see what I get. So I did that. I counted up all these dashes, and there were 30 of them. I actually started, this is 0, so 1, 2, 3, 4, 5, and I went all the way, and there were 30. I'm like, all right, there's 30 dashes. I have 10, really 11 data points if I talk about 0, but I did 30 divided by 10. And so basically, about every 3 lines, I had a number, right? And I just went by ones, since my data is very clean in the sense that it just goes up by 1 each time. This worked. There's a kind of a rule that you're supposed to fill up the space that they give you. So if this is our space here, if this is the amount of space that we have, then this is what we're supposed to use. So that's how that works. I then need to figure out what my scale is for the y-axis, okay, and it needs to go from essentially 0 up. It needs to, all these dashes need to include numbers from 0 to 200. I can go above 200, but it needs to include all that. So once again, I'll probably sit there and count them and try to figure out, should I go by 2s, by 5s, by 10s? Like down here, I went by 1s, but I skipped a few blanks because I wanted to fill the whole space. So here, how would you do this? Did you go by 5s? Did you go by 10s? Sometimes I just sit there and I go 10, 20, 30, 40, 50, 60, 70, and I just try to see would it all fit in there. So I went through here and I just said, okay, cool. It looks like every other space I would do, I'd put a number in and it looks like it goes cleanly from 0 to 200. So that worked out. Okay, sometimes it works, sometimes it doesn't. This is one of those things you should probably use a pencil, right? Because if you mess up, you want to erase, try again. All right, so now I'm going to put a data point where these two things intersect. So at 1 and 20, so here's 1 and there's 20, right? So I would go up here and I would go over here until the two intersect, right? And I'd have a data point, and that's how that would go. 2 and 40. 3 and 60, and this is where they intersect, and I'm not perfect. So 4 and 80. 5 and 100. Alright, so there's all my data. What can we infer from this? What can we figure out? You guys have had some math classes. I hope that you understand that this is a positive relationship. As time goes up, displacement goes up. So as time goes up by 1, displacement goes up by 20. Time goes up by 1, displacement goes up by 20. 1, 20, 1, 20. Okay. This looks like a linear function. Ooh, there's that word function. What does that mean? It means it's a linear relationship. It will make some sort of a straight line. Let me show you what we don't do. We do not connect dots. So we don't do this. We're not doing that. We don't connect dots. That's what they do in like junior high or something. We're not going to connect dots like this. And you see how I'm not perfect. So my line isn't even completely straight, right? We draw what's called a best fit line. And a best fit line, what happens is you take your data, however perfect or imperfect that it is, and you're going to try to get that line to go through as many points as you can, but you want it to be about half the points to be above the line and half the points to be below, and it's not going to be perfect. It's called a best fit. It's an approximation. So there you go. So there's my best fit line. Okay. What's the slope of this line? All right, that's a math question in the sense that what is the slope? Slope is rise over run. What I do is I pick 2 points. I usually don't want those points close together. I usually want to pick 2 points kind of further away. And I'm going to do change in y over change in x. So, I may pick, let's pick 2 points. Pick this point here. I can pick this point right here. So I'm going to do change in y over change in x. So what I'm going to do is, what this means essentially, is I'm going to take my pencil. I'm just going to see where, I'm going to draw a real sloppy line here over to the y-axis. See where it hits the y-axis. It's like 180 for that dot. For this dot, Draw a line over. Oh, it hits 80, right? So my change in y is going to be 180 minus 80 is 100. That's my change in the y-axis. I'm going to do the same thing for the x-axis. So here we go. So here I go. Looked at the x-axis, right? This was my second point. How do I know this is x2? This is my second point because it's further along in time than this point, right? 9 seconds is after 4 seconds. So this has to be my second point. 9 and then 4. 9 minus 4 is 5. 100 divided by 5 is 20. So what's the slope of the curve plotted? It's 20. And that's what you would do as far as a math course, right? Now, physics slope means something. It has a meaning. So what does our slope mean here? Well, we're not just dividing numbers. We're taking the y-axis and dividing by the x-axis. So what I do is look at what is my y-axis. It's displacement, which is measured in meters. What's my x-axis? It's time. Time is measured in seconds. So what's the slope of this curve? Well, it's 20 meters per second. Of course, what is that? Well, that was the velocity of our car. It was a constant speed, so we got this straight line. When you see straight lines, it means something is constant. So you need to know this. If you see a straight line, something is constant. In this case, our slope is constant. What does that mean? That means after every second, the displacement is the same, which means I'm going the same speed every second. So I have constant velocity. Okay, so that whole thing was really just a review of displacement and time graphing because that's what we did. We actually plotted displacement and time, and that's was the whole last video. Now, what you're going to do next is take the same data and try to graph velocity in time. So this is a different graph. I'm going to take the same data, okay? So the first thing we got to do is we have to fill out our data table here. So after 1 second, right, what was our velocity? Our velocity was constant. Velocity wasn't changing. So after each second, it stayed the same, right? Our car is set on cruise, so it's 20 meters per second. So after 2 seconds, what's the speed? Still 20. 3 seconds, still 20. 4 seconds, right? I'm lazy, so I'm just going to do this. So there you go. It's 20 meters per second every second. Okay, now we got to graph it again. So I got to do my I got to come up with my scale. I'm going to use the same time, the same scale for the time as in the last one. Okay. Boom, there you go. There's all my times, same as before. Now I got to have some type of scale over here. Well, here's the deal. My velocity, which is going to be on my y-axis, doesn't change, right? So kind of cheat here. I'm going to pick a line, and I'm just going to call it 20. So here you go. Plot all my data, right? What kind of relationship is this? It seems like we're going to get a flat line, right? So if I create a line here, start right there, and run over here, it looks pretty flat to me, right? So as time goes up, as time goes by, what happens to my velocity? Well, it stays constant. It's constant speed. What's my slope here? Well, I have a run, but I don't have a rise. Nothing goes up. There's no change in the y-axis. So my rise is 0 every time, which means my slope is 0. Now we said that slope actually means something. So in physics, slope means something. So here I'm taking meters per second, a speed, and dividing by time in seconds. So my slope is meters per second per second. The heck is that? Meters per second is called acceleration. Fact. The slope of a velocity time graph is acceleration. What is acceleration? What does that mean? Well, that's a loaded question. We got to get into that. Obviously, it has something to do with dividing a velocity by a time. What it means is your velocity is changing per unit time. Here, if our slope is 0, then our acceleration is going to be 0. We get a flat line, which means we're not speeding up, we're not slowing down, we're cruising.